Hello everybody, Justin Miller, Oxnard College Physics here. We are going to be looking at sources of magnetic fields today in this segment. So what we want to look at is ultimately something we've seen before. I can take some wire here, battery here, got a nice magnet here. You know what's a magnet? Because it picks up things that are magnetized. And I can take it and notice that it doesn't do anything with this wire. Copper's inside this wire, generally not magnetizable, so it doesn't do anything, right? So then we go ahead and plug this in, complete a connection, and now that we assume that there's electrons cycling around, substantiating some amount of current, and I bring this in again, and oh, look at, I can get attraction, I can get repulsion. All of a sudden we do get some interaction, but it's either. It's not just always attracted, like iron's always going to be attracted to magnet. So what's the deal with this? Well, the deal is what we could do is we could take ourselves a little compass. You're not going to be able to see this, but I got to take my word for it. I can lay this compass like this, and it tells me that magnetic north is that away. Very good. Well, what happens if I put this little compass in the vicinity of this current carrying wire? Now it says north's that way. Huh, that's weird. What does that mean? Well, it ultimately means that this wire is producing a magnetic field. And that also explains the interaction of it with a magnet in terms of an attraction and a repulsive force acting on it. So we ultimately get from this that currents themselves produce magnetic fields. Moving charges produce magnetic fields, which ultimately explains the interactions of moving charges with magnetic fields themselves. So what we want to do is explicitly get some expressions for the magnetic field due to current carrying wires and take a look at this. So, grab a couple pens here. And what we're going to start off with is what is known as the Biot-Savart Law. The Biot-Savart Law is ultimately a statement about magnetic fields and what they're due to. So the Biot-Savart Law says that dB hat is equal to mu 0 I over 4 pi r squared multiplied by ds hat cross r hat. That is the Biot-Savart Law in a little nutshell there. So what do we have here? Well, we've got ourselves that dB hat is the magnetic field element due to the current I within an element ds hat and r hat is position vector unit position vector. Pointing from the current element to the position in space in which are determining dB hat. R is the distance away. So we've got the unit vector that points from the location in space of the current element in that ds hat to where we're actually trying to discern what the magnetic field is. So commonly, we look at something like this, and what we could do is say that there's some current, grabbing the same color pin here. There's some current within this, we'll say, wire here. And what we want to do is look at some position in space. And say, what is dB hat there? What is the magnetic field element due to? Well, due to a particular current element. So we can take ourselves, for instance, some little infinitesimal element, line element in which that current resides, and say, well, we've got ourselves that current element there, and we've also got ourselves a position vector, unit vector that points. That's probably a little too big, but it doesn't really matter. We've got a unit vector that points to that position in space, and then the actual distance between the current element and the position is r itself. And we get that the magnetic field vector element is substantiated by this cross product relationship here in terms of its directionality. So we've got ds hat crossed into r hat gives us the direction of dB hat. So this is what you got to think about doing. You got to think about taking these infinitesimal current elements, in a sense, and figuring out the overall contribution that they produce in terms of all these dB hats at one location in space, and add them all up to figure out what the magnetic field is at that particular position. The point with this is that depending on where you are, you're going to have different distances away. You're going to have different orientations with respect to ds hat and r hat, and you're going to have different magnetic fields then. So this ends up being fairly complex, but what we can do is look at some special cases in which the magnetic field overall is fairly well behaved and easy to extract out. So this is what we start off with, our Biot-Savart Law. So first off, what would the direction of the magnetic field be at this location, the magnetic field element dB hat, at this location due to this current element? So we go back to cross products, right? We have been using fingers, palm, resultant vector is the thumb. We'll just stick with that. There's many variations of it, but fingers, palm, thumb, that works pretty good. So we could put our fingers in the direction of ds hat, which is tangent to the line or tangent to the wire. So we've got our fingers in that direction, and then we orient our palm so that it's facing in the perpendicular component of, or facing the direction of the perpendicular component of r hat, which would be, well, the perpendicular component of r hat would be up that way with respect to ds hat, and our thumb's left in the direction of the magnetic field. So we get that the magnetic field's direction at that location in space would actually be outward due to that particular element there. So that's something else that we need to be able to keep track of, is the directionalities when we're adding up the overall contributions to all the current elements housed within the wire. Sounds fun, right? You're right, it is. So let us go ahead and take a look at a nice case where we just got a segment of wire so that we can start looking at what the magnetic field is at a specific location in space due to that current segment. So let me erase this here. Start off with this. We'll put magnetic field due to a straight current segment. So we can take some wire that has some current in it. We'll say that it has some current I in it. Great. And we're just going to pick a spot, pick a location in space in which we want to determine what the magnetic field is. Now, where we pick is sort of irrelevant. We pick somewhere. I'm going to pick above this wire in the plane of the board, and I'm just going to pick sort of a spot like right here. And say, we want B hat here. Want to know what is the magnetic field at that particular location in space due to the current in this wire itself. So what can we start doing? Well, start figuring some stuff out, shall we? All right, so first off, let us say that this particular point is a distance A away from the wire itself. Shortest distance A away, cylindrically radial distance. And then we can go ahead and start putting in some other things corresponding to this particular wire, like, hey, make some triangles with the ends. And what we can do with this is start to get an idea of the contributions of these different amounts of, well, different locations, current segments, we'll say. So we can take ourselves and say, well, right here, there's some little dx hat. We'll just say that this is along the x-axis, makes things easy. So put some x down here. Got some dx hat in which that current is contained. So this is taking the place of our ds hat in a sense. So just write that down. Well, we've got that little element there is some distance r away from this. And furthermore, we've also got a nice little r hat regarding that element in terms of its contribution to the magnetic field. So what do we want to do with this? We want to figure some stuff out. So first off, let us think about what the direction of the magnetic field, what it will be at this particular location in space. So we're going to have that all our current elements, or all our line elements, are always pointing in that direction. So no matter what, that's going to be the direction of our ds, or dx hat. R hat is going to vary as we sweep over here, pointing like this, always pointing to that location in space. But we're really only interested in the perpendicular component of this unit vector here. And the perpendicular component with respect to that way is up. So what do we get out of this? Well, we get out of this that we're going to have our dx hat that way and our r hat that way, which will mean that every infinitesimal contribution of the current will produce a magnetic field that is out of the board. All of them. That's nice. So we can already say that B hat is out of the board above the wire. So what can we do with this then? Well, we can start doing some nice things with this, because ultimately now we've already noted what we need to be picking out. We don't need to be picking out that particular component there. We could call that the z hat component. X, Y, Z. That would be perfectly fine. So let's do this. We have B hat itself is going to be, well, correlated with integrating over that Biot-Savart Law. So we're going to get rid of that dB, just turn it into B hat. We've got this. We've got that it is mu 0 I over 4 pi r squared ds hat cross r hat. And well, we want to integrate over the total displacement, excuse me, the total line element here. So we're going to change this around a little bit and start embedding some things that we have in here. So first off, we could resolve this cross product here because we already know the direction and we can get something nice out of this. So let us write this. The magnitude of b hat is going to be equal to the integral of mu 0 I over 4 pi r squared. And then we know how to deal with cross products in terms of magnitudes. That's just going to be ds times the sine of a theta, where theta is the angle in between ds hat and r hat. This is a unit vector, just has a magnitude of 1. So we get that this portion right here ends up being ds multiplied by the sine of theta. And we can take the absolute value of this, just because again, we're only looking at the magnitude here, and say that this is in the k hat direction. It's in the z direction. If x is that way, y is that way, then z is out of the board that way. So this is how we start doing this. What is this angle theta? The angle theta is the angle between this dx and this r hat. So really we could change this ds to a dx, which we will here momentarily, but we've got this theta right there. So that's a good. So we can change this ds to dx, and note that we're integrating from, well, some initial x to some final x. That's great, but there's some other things that we could do with this. We could also go ahead and define this angle right there and call that some angle phi. And note that the sine of theta is equivalent to the cosine of phi. There's a reason that we're going to do that. That ends up being that it's the easiest integration to sweep across an angle phi and go across the total line here. So that's exactly what we're going to do. So we know that the sine of theta is equal to the cosine of phi. And again, that ds is equivalent to dx in our particular case. So that's good. We're going to go ahead and rewrite this really quick and say that the magnitude of b hat then can be the integral of mu 0 I over 4 pi r squared ds times the cosine of phi. But if you notice here, we've got 3 different things that are going to be varying with respect to which element we're looking at. We've got the elements themselves that we're integrating over. This should be an x, sorry, dx, so we're making that change. We've got the line elements, dx, that we're integrating over. And we've also got this phi right here that's going to be changing as we move across this line. And we've also got this distance r here, which is the distance from the element under consideration to the point, which goes from, well, this r right here to a, and then starts increasing back to some other values. So in order to integrate this in a coherent manner, it is best to go ahead and have one thing that's varying. So if we just need to build up some relationships with respect to these things and figure it out. So we want to really, in this particular case, rewrite r squared and rewrite dx in terms of phi. So we got one nice variable that we're going to integrate over, and then we can worry about this. So let me go ahead and take the absolute value of this. Really, this is k hat. It's noted in the direction. Anyways, what can we do? Well, let us take just this little segment right here and look at some of the geometry that we've got going on. So we've got an A, we've got an R, we've got an X. That sounds pretty good. And then we've got that phi right there. So let's make some sort of associations with A is just some constant symmetry radial distance away from the wire that we are, that distance A. R is varying and phi is varying. So let's rewrite R in terms of phi and A. So what do we got? Well, we can write that the cosine of phi is A divided by R, adjacent over hypotenuse. So let's do that. Cosine of phi is equal to A divided by R. Thus, we have that R is going to be equal to A over the cosine of phi. And R squared then is equal to A squared over cosine squared phi. So that's a nice one to have. It's not that good. And jump and get a pin. And what else do we want? What about X? Well, let's see here. We've got X. We want to rewrite that in terms of something with phi and A. Let's look at tangent, right? The tangent of phi is opposite over adjacent. So let's write this. We've got also the tangent of phi is equal to X over A. That's great. What happens if we go ahead and solve that for X? We've got that X is equal to A times the tangent of phi. That's a fantastic, but we don't want X really, we want to know what dx is. So let's do this. Let's look at how X changes with respect to phi. So we can write that dx by d phi is equal to, well, A times d by d phi of the tangent of phi. I pulled the A out because A is just a constant. So this is what we get. We've got this going on. Do we know what the derivative of the tangent of phi is with respect to phi? And the answer is, of course we do. That's secant squared phi. So from this, with a board going on here, we've got ourselves from this that dx by d phi is equal to A times the secant squared of phi. And then what can we do? Multiply both sides by d phi. And we've got ourselves then that dx is equal to A secant squared phi d phi. And there is our dx. So we've got r squared, great. We've got dx, great. We can write this all in terms of phi now. So we go back up to our expression for the magnitude of the magnetic field and we'll rewrite this. We've got the magnitude of the magnetic field is going to be equal to, well, mu 0, I, and 4 pi are all constants. Mu 0, the permeability of free space, 4 pi times 10 to the negative 7, Tesla meters per amp. That's great. We're just going to pull all that stuff out. So we've got a mu 0, I is the current, over 4 pi multiplied by the integral of, well, we've got a cosine of phi. So let's write that one in there. Cosine of phi. And then we've got ourselves a dx. Well, dx is A secant squared phi d phi times A secant squared phi d phi. And then we've got ourselves that r squared term divided by r squared. Well, r squared is A squared over cosine squared phi. So we've got ourselves this, A squared over cosine squared phi. And what are we integrating over? We're integrating over phi. We'll get to the limits of integration once we've got this all worked out here. So what can we do with this? Well, we can notice that one factor of A goes away, cancels that out, and A is just some constant that's determined by how far away we are. We pick that. So we can factor an A out. And then we've got all this cosine squared, secant squared stuff going on. Well, look at this. We've got secant squared phi right there, and then we've got divided by the quantity of 1 over cosine squared phi. Well, 1 over cosine squared phi is the same thing as secant squared phi. So we'll have secant squared divided by secant squared, which just goes away, just leaving us with this cosine of phi right here. So in the end, we are getting ourselves that the magnitude of b hat is going to be equal to mu 0 I over 4 pi. I'm going to pull this A out because that is just a constant value. And then we've got the integral of the cosine of phi d. That reduced a whole bunch. And moreover, that's a really easy integral to solve, right? The integral of cosine is just sine. So that's nice. So fantastic. All that's left to do is decide what our limits of integration are. And notice something about this. Unlike the case where we're looking at the electric field due to a current segment and we stuck with being above the midpoint, we're not above the midpoint of this wire here. it's not necessary because the magnetic field's all in one direction if we're above this wire. Whereas when we're looking at the electric field due to, it wasn't a current, but it was just due to a line charge density, lambda, we got that if we weren't directly above or aligned with the midpoint, that we would have both x and y components. And that complicated things a little bit. This is all one-dimensional though. Fantastic. At any rate, let's just go ahead and do this. We are going to throw in some limits of integration. And note that this is what we're really looking at. We can take our point here. We can take our line there. We can take from the ends, and we could call this some phi 1, and we could call this some phi 2. And note that we go from phi 1 to 0, and then from a 0 to phi 2 in opposite direction. So this is, it's a little bit weird with the limits, but really this just breaks up into two things. We go from phi 1 to phi 2, but you have to be utilizing a proper sort of sign convention with this. So we're going to call phi 1 positive and phi 2 negative in this particular case, so that things look grand. At any rate, we've got this now. We've got this is going to be equal to, let's go ahead and say the magnitude of b hat is going to be equal to mu 0 I over 4 pi times a multiplied by the sine of phi evaluated from phi 1 to phi 2. And really which way you go kind of doesn't really matter. But at any rate, what happens with this? We just got the sine of phi 2 minus the sine of phi 1, which means that one of them has to be called negative. Sweeping one way and sweeping the other gives a negative sign overall. And what's typically written here then is this is mu 0 I over 4 pi times a multiplied by the sine of phi 2 minus the sine of phi 1. And we let phi 2 be a positive angle and phi 1 be a negative angle. Because they're on opposite sides of what we're calling the 0 degrees right here. So we've got positive and negative. We can switch the signs. One's positive, one's negative if you're on opposite sides of the 0 point. That's it. So there we go. Really, overall, it's best if we just take the absolute value of this, because this is just the magnitude, and depending on what you're calling phi 1 and phi 2, you could end up with something that comes out negative. We don't want that, so that's the easiest way to deal with this. All right, so what do we get out of this all? We get ourselves a nice expression. This is it right here. This is it. There's the magnitude of our magnetic field at distance, radial distance away, A, from a current segment in a straight wire. And that's pretty much that. Here's another question though. Before we proceed and look at the problems, what if the wire is infinitely long? That seems kind of a nice question, looking at some limiting case here. What if the wire is infinite in length? What we got to do is go ahead, draw this out. Note that these extend out to infinity, negative infinity. We pick ourselves a point. That's great. We're some distance A away from this infinitely long straight wire. And what do? We ask ourselves, well, what do the angles look like when the ends are infinitely far away? So what do we have? This really is going this, and this is going like this, which gives us a 90-degree angle. Well, in terms of our expression here, one of those is positive and one of those is negative, being on separate sides as we sweep through those angles in the integration. So let us just say that phi2 is equal to 90 degrees and phi1 is equal to negative 90 degrees. We've got the sine of 90 is equal to 1. The sine of negative 90 is equal to negative 1. So the sine of phi2 minus the sine of phi1 will be equal to 2. What does that give us? Well, we just multiply that front part by 2, and we've got that the magnitude of the magnetic field due to an infinitely long wire is going to be equal to mu 0 I over 2 pi times A. And what we can do is we can utilize this infinite approximation as long as we are locally close to the wire. That is, the distance that we are away from the wire is much, much smaller than the distance to the ends of the wire. And in that approximation, this holds to be pretty valid there. So we're going to use this for long straight wires. Then in terms of the direction again is gotten by the cross product relationship between, it's really the direction of the current and the position in space in which we're trying to identify what the magnetic field is. So if the current in this were going this way, I would have fingers in the direction of the current, palm positioned in the direction in space in which I'm trying to determine the magnetic field. My thumb points in the direction of the magnetic field. So if the current's going this way and I'm looking above the wire, the magnetic field is out of the board. If the current happened to be going this way, well, I would have the current's going this way. I'm looking up above it, magnetic field would be into the board. Likewise, if we're looking down below, the current's going that way, down below it, the magnetic field would be into the board, and if the current was going that way, and we're looking below it, the magnetic field would be out of the board. So it's very important directionally to be very aware, just in general, of where do you want to know the magnetic field, because the direction depends. So let's look at one final thing here with respect to that. And we can kind of do this. So let's take ourselves a current. That's directed into the board. From a long straight wire. I say, well, what's the direction of the magnetic field? And the first question is, where do you want to know what it is? It depends. So I can pick some region in space and say, you know what, I want to know what the direction of the magnetic field is right here. Well, what do we have? We've got the currents going into the board, and then the position vector, the unit vector, points from the current element to the position in space in which we're trying to determine the magnetic field. So if I do fingers into the board, palm oriented facing that position in space, I get that the magnetic field in this particular case is that way, perpendicular to the radial direction. So in this particular case, for this particular location, the magnetic field would be in that direction. It would have a magnitude mu 0 I over 2 pi A, where A is the distance away, but there's the direction of it. Well, if instead I said, you know what, I actually want to know what the direction is right here. In this particular case, we've got a different position vector. The unit vector now points like that. Current's going into the board. We orient our palm facing to the position in space in which we want to know the magnetic field, and we get the direction of the magnetic field. In this case, that direction is like that. What we end up getting, in a sense, is that we can think of this current being surrounded by concentric circles, and the magnetic field has to lie tangent to those circles. And then it's a matter of tangent which way, that way or that way. Just go back to the right-hand rule. Current crossed into position gives us magnetic field. So it's going to be something really important to be able to have a good hold of and utilize. All right, that's it.